Suppose your transmitter is designed to generate only 100 megahertzes. Why does your spectrum analyzer also show signals at 200 megahertzes, 300 megahertzes, or even 400 megahertzes? Where did these extra frequencies come from? They're called harmonics. In the previous lesson, we introduced the spectrum analyzer and learned how it displays signal power across the frequency spectrum. Engineers often use it to verify that transmitters produce signals at the correct operating frequency. However, practical measurements frequently reveal additional peaks located at multiples of the desired frequency. These unexpected signals can reduce system performance and interfere with other communication systems. This raises an important engineering question. Why do practical electronic circuits generate frequencies that were never intentionally transmitted? A harmonic is a frequency component that is an integer multiple of a signal's fundamental frequency. If the fundamental frequency is f, then the second harmonic occurs at 2f, the third harmonic at 3f, the fourth harmonic at 4f, and so on. An ideal sine wave contains only the fundamental frequency and therefore produces no harmonics. Harmonics appear when a signal is distorted by nonlinear electronic components, such as amplifiers, mixers, or power devices. Intuitively, imagine striking a guitar string. Although you hear one musical note, the string naturally vibrates in several modes at the same time. These additional vibrations produce harmonics that give each instrument its unique sound. Electronic signals behave in a similar way when distortion is present. Physically, consider a power amplifier transmitting a 100 MHz signal. If the amplifier operates outside its linear region, the output waveform becomes distorted. On a spectrum analyzer, additional peaks appear at 200 MHz, 300 MHz, and higher multiples of the fundamental frequency. These are harmonic signals created by the amplifier's nonlinearity. Mathematically, nonlinear waveforms can be represented as the sum of multiple sinusoidal components using the Fourier transform. The stronger the waveform distortion, the more energy appears in the higher-order harmonics. Harmonics are an important consideration in RF transmitter design because they can interfere with nearby communication systems operating at different frequencies. Regulatory standards strictly limit harmonic emissions to prevent unwanted interference. RF engineers reduce harmonics by keeping amplifiers within their linear operating region, carefully selecting circuit topologies, and using low-pass or band-pass filters to suppress unwanted frequency components before transmission. Every wireless device, including smartphones, Wi-Fi routers, satellite transmitters, and radar systems, must control harmonic emissions before it can meet regulatory requirements. Understanding harmonics helps engineers recognize that practical circuits rarely produce perfectly pure signals. Identifying and controlling harmonic generation is essential for maintaining signal quality and ensuring electromagnetic compatibility. A common misconception is that harmonics are caused by multiple oscillators operating together. In reality, harmonics are usually generated by nonlinear behavior within a single electronic circuit processing one fundamental frequency. In the next lesson, we'll explore intermodulation products and discover what happens when multiple frequencies pass through a nonlinear device at the same time. In this lesson, we learned that harmonics are integer multiples of a signal's fundamental frequency and are typically generated by nonlinear circuits. We also saw why harmonic suppression is essential for transmitter performance and regulatory compliance. In the next lesson, we'll explore intermodulation products and see how nonlinear devices create entirely new frequencies when multiple signals are present. If you found this useful, like the video, subscribe, and follow for the next lesson.